In this video, we're going to look at computing complex eigenvalues and eigenvectors associated with them. So let's start with a matrix, and it's just going to be a 2 by 2 matrix. We don't need a very large one to figure out what we're supposed to do here. So we'll go ahead and find the eigenvalues just like usual. We'll take a minus t times I to find our characteristic polynomial, and we'll have 3 minus t, 1 minus 2, and 1 minus t for our elements then, and we go ahead and compute the determinant. So the characteristic polynomial, p of t, is computed as 3 minus t times 1 minus t minus negative 2, and simplifying that, we get that p of t is equal to t squared minus 4t plus 5. So now we have our characteristic polynomial, which we would then factor. In this case, we would have to apply the quadratic formula since it doesn't factor, and that would produce two eigenvalues, both of which are complex. So 2 plus or minus I are the eigenvalues that are associated with this particular matrix A. So far, there's really nothing different that happens other than lambda turns out to be a complex number. Now, to find the eigenvectors, we go through our typical process of replacing one of the lambdas into the homogeneous system. So let's take lambda equal to 2 plus I and work through this side of it, and I'll have you guys work the second half. So let's plug this in, and we get a matrix that looks like the following: 3 minus 2 plus I, 1 minus 2, and 1 minus 2 plus I. So there's our matrix. And we'll go ahead and simplify down these expressions just a little bit. So let's rewrite this again. It's going to look like 1 minus I minus 2, 1 minus 1 minus I, and here we'll put it into the homogeneous system as we would typically do. So now the trick is to go ahead and somehow simplify this down using row operations, but of course now we've got complex numbers in here. So there's one particular trick that we want to use, and that is to multiply by the conjugate of one of these complex values. So I'm going to multiply the first row in this one by 1 plus I, which is the conjugate of this element here. So we'll go ahead and put in a 1 plus I times that first row and see what the result is. So we end up with 2 and 1 plus I and 0 as our new first row. And the second row then is minus 2 and minus 1 plus I when we factor out negative 1 and 0. And much like we would expect when we're solving for these eigenvectors, one of these rows is clearly a multiple of the other. So what we really end up with now is a system that looks like 2, 1 plus I, and 0, and then a row of zeros along the bottom. So the implication then would be that 2x1 plus 1 plus I x2 is equal to 0, and then of course we can take x2 to be a free variable and rewrite this one more time and get it into a vector form. So solving out for x1, we have that x1 is going to be equal to negative 1 plus I over 2 times x2. Of course, again, x2 is equal to x2. And then in its vector form, the vector x comes like minus 1 plus I over 2 and 1 times x2, which is fine, but I think it's probably more useful for us to just go ahead and scale this really quickly by multiplying by -2 and keeping the values within the vector a little bit easier. So we'll go ahead and do this one more time and say that x then is going to be all scalar multiples of the vector 1 plus I and -2. So now we have the eigenvector that corresponds to the eigenvalue that we started with, which was the 2 plus I eigenvalue. And that's how we could do that. So I leave it to you to solve for the other eigenvector that goes with the eigenvalue of 2 minus I.